All right. So let's move on to the low temperature limit then, which is more subtle. So it'll turn out that, so remember that, we approximated this sum by this integral, right? But because of this factor, this approximation doesn't take into account the contribution to the sum from the ground state. And in the low energy limit, we shall see that this is going to be a problem. So let's just first carry on without, fixing this problem, and then see what happens, and then we can fix this problem. Okay, so let's look at the number of particles n over v, and as before we saw that it's given by 1 over 4 pi squared. This is the exact definition. Now we can just break up beta and put 1 over kbt instead. Now divided by h bar squared, and this is going to be in 3/2. And then we have an integral from 0 to infinity d of x to the power half divided by z inverse e to the power x minus 1. Now, this thing is going to be right. So this thing is going to be 1 over lambda cubed. And this thing we are going to define as g 3/2 of z. Okay. Now note that this has nothing to do with g of e. Okay. There's nothing to do with g of e. It's a different function. And g of n of the fugacity is defined as 1 over gamma of n, which is the gamma function, and then 0 to infinity of d of x to the power n minus 1 divided by z inverse ex minus 1. Okay, this is the definition of g, and here in the calculation of n over v, we get to use g 3/2 of z. When we calculate the energy, we have to use g of 5/2 of z. Okay. So now, when we took t infinity, then lambda went to 0, right? So that in that case, what happened was that 3/2 of z, that went to 0 in such a way that n over v remained constant. But now what we're going to do is that we're going to take t going to 0, which means that lambda will go to infinity. Now, is g 3/2 of z going to remain constant like before? Because we want to keep the number of particles fixed, because that's a physical That's our physical, condition. And we'll see that because we ignored the ground state in the integral, that's not going to be the case. So before we do that, let's re-express g of n in a different way. So g of n is 1 over the gamma of n, then d of x, z x to the power n minus 1 e minus x divided by 1 minus z e to the power minus x. Okay, so this thing can be expressed, the denominator 1 over the denominator can be expressed as an infinite series, right? So we can express this as, well, let's get the z out, then gamma of n, and then we have d of x 0 to infinity, and then we have x to the power n minus 1, then we have e to the power minus x, and then this is a power series which goes from 0 to infinity, z to the power m, e to the power minus mx, right? This is a binomial expansion. And then what we can do is that we can now take this, multiply in, take this, multiply in, and then we express the result in a way where we just are missing the m equals to 0 term. So this, and then becomes m plus now the sum goes from m equals to 1 to infinity. Now z goes m, and then okay, let me yeah. So this is not there yet. Then d of x, and we have x to the power n minus 1, e to the power minus m of x. Okay, is it clear how we did what we did here? Because if I multiply this with this becomes z to the power m plus 1. And if I multiply this, that here we have minus e to the power minus bracket m plus 1 times x. So m equals to 0 can be replaced by m equals to 1. Okay, that's what we've done here. And this remains the same. And then what we can do,
Sir, a bit earlier you said t tends to 0 and the wavelength is infinity, right?
so what tends to 0?
Would you scroll up a bit?
Yeah.
Yeah, t tends to 0, lambda tends to infinity. So lambda is the wavelength, right? So how does the infinity wavelength uh, represent in the physical world?
Well, what means that it becomes large, and therefore the quantum effects are not localized anymore.
Sir, what is the meaning of localized?
Meaning that the quantum, if the wavelength is small, then for if you're looking at, well, localized means that the fact that there's a quantum particle around cannot be ignored, so to speak. The wavelength becomes large. That's all I mean. It's not infinite, of course. Like if your gas is in a box of particles, the wavelength becomes large, meaning that the particle can be found anywhere in the box.
Oh, got it.
Okay, good. Okay, so then we can do is that we can just do another variable change, and that variable change is going to allow us to write this as m goes to 1 to infinity, and then we have z to the power m divided by m to the power n, and here 0 to infinity du, and u to the power n minus 1, e to the power minus u. So this is going to be u. This is my new variable. But this thing is nothing but gamma of n. And therefore, this thing and this thing cancel out. And therefore, we can write Gn of z as sum over m equals to 1 to infinity, z to the power m, m to the power n. Now, we will be interested in g of n when z is 1. In that case, this thing just becomes the Riemann zeta function, okay? And for g 3/2 of 1, this is zeta of 3/2, which has some value. The value is 2.612. Did anyone know the value of zeta 3/2? I guess not. I didn't either. I used to have a student who used to know these things. All right, so so now let's look at n over v again. So n over v with this define this function is remarkably simple looking because we have hidden all the complication. Now, as t goes to 0 and lambda goes to infinity, z goes up to 1 and g of 3/2 also increases, okay? But we know that z can never go beyond 1. It can never reach 1. It has to be less than 1. So that means that as we lower the temperature at the value of z equals to 1, we reach a critical temperature. And the critical temperature, just by inverting that relationship, is just 2 pi h bar squared kbm, and then n divided by zeta 3/2 v 2/3. So what happens below that? So suppose that this has reached z had reached 1, and and we are increasing this such that this has reached 1, and we reach the critical temperature. But we want to keep this constant. So if we want to go beyond that, then this cannot change because z cannot be increased anymore. That means as we now increase z, n will start falling. That below this critical temperature, the number, so below this critical temperature, the number of particles n will decrease. But that is contrary to our assumption. The best that can happen is delta n over n, but in the thermodynamic limit, that is extremely small, and that's not what we are talking about. So something must be wrong. And as we discussed before, what's wrong is that the the occupation number of the ground state has not been taken into account. Now, if I do that, then the total number of particles, which is v by lambda cubed g 3/2 of z, now has this extra term. This comes from the fact that the occupation number of the vacuum is this. Now, because of this term, we can keep on, decreasing lambda, but in a way such that this thing now diverges, so that this now remains constant. Okay, so this is uh, the 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 solution to the conundrum, and then you can say, okay, what is the fraction of the particles that are in this ground state of the total particle, and that can be very easily shown. Just a few lines of algebra, I think. N lambda cubed 3 halves, and that is 1 minus T over Tc 3 halves. And as you can see, as you lower the temperature, more and more particles will um, more and more particle will be in the ground state. In the absolute zero temperature, it's actually 1, right? All the particles. And this phenomena, in which at very low temperature, all the particles of your gas, of your bosonic gas, coalesces into one state, the ground state, this is known as Bose-Einstein condensation. Okay, and unfortunately, we have run out of time, and we can't really discuss more of the properties of this guy. Maybe after the Eid holidays, we can discuss this without being included in the exam. Okay, so any questions?
Sir, does the Bose-Einstein statistic uh, relevant for solid or liquid or plasma?
It's for liquid. It's for in fact, there are like superfluid helium. The superfluidity comes from the fact that it's actually a Bose-Einstein condensate, and therefore the whole macroscopic fluid acts as if it's in one. It's basically one molecule, and therefore there is really no friction, and the superfluidity comes from that. Okay.
No internal friction.
Sorry.
Like no friction between the molecules.
Yeah, exactly. And it's only Einstein predicted it like in the 30s after Bose did his work, and it's only in the 1990s, that this was experimentally verified, and a Nobel Prize was given on it. Okay.
I
All
have a
right. So
question about these kinds of long derivations that we've been doing for the last few classes with their
yeah,
big integrals and stuff. How much of this are we supposed to know intuitively, like all of the steps, or do we need to know just the results? I'm not sure.
I think you need to understand it. That's all. You shouldn't memorize these things, right? I mean, if you understand it, you'll forget it at some point. But at some point, when you need it, you'll be able to go back to a book, pick up a book, and say, "Oh yeah, I learned this, and this is this, this is that." But, yeah, try to see if you understand the story, and that's really what's important. When you're reading it, when you're studying it, yeah, do work it out, because that means that you're grappling with the mathematics. But there's no reason to memorize anything.
I mean, not memorize, but I was saying more like follow the entire derivation step by
Yeah,
step.
you should be able to follow the entire derivation, and I mean, this is taken from from David Tong's lecture note. So I have like skipped steps and stuff like that, and I have presented in the way that makes sense to me. But if you want to, you can always go back and read that, and I encourage it.
Okay,
Okay, but
understood.
yeah.
Sir, so the Riemann zeta function, is that just a function, or it has some related? Is it something related to physics of the nature?
Well, Riemann zeta function turns up a lot in quantum physics, and it turns up a lot in when you have to do counting of uh, ground state stuff. And in fact, it turns out in the computation of the vacuum energy, of the Casimir energy calculation. It turns up in the calculation of the dimension of space-time in string theory. So it's kind of a mysterious why it shows up so much. But yeah, it has many and many, it seems to be there a lot in quantum mechanics, in many body quantum mechanics. So, it's a mysterious object. I mean, as you know, there's a very famous unsolved puzzle associated with the Riemann zeta function, right? The Riemann conjecture is that all its zeros lie on a particular line, and
So the
nobody's been able
Millennium
to
Prize
fix it.
problem.
Yeah, there's also a $1 million. I mean, this is way bigger than that $1 million, because there are literally like hundreds of tomes written. There are theories based on the assumption that that is true. And many famous mathematicians have tried to prove it and failed, including Michael Atiyah towards the end of his life. Michael Atiyah, who is famous for his many contributions to geometry, and he even won the Fields Medal at an early age.